Okay. All right. So, um, we want to review plotting complex numbers. So this is a complex plane. And the thing is, if you look at any complex number, let's say a plus bi, right? A and b really don't communicate. Like if you add a plus bi, and if you add, like, let's say another complex number, let's say c plus di, b and d, and I mean, you're gonna get a plus c plus I times b plus d, right? You are not going to get any like sort of interaction between the real part and the imaginary part. So what we do is we can plot these complex numbers just like real numbers. You can plot on the real number line. For the complex numbers, imagine the real number line. Imagine lifting it up, rotating it 90 degrees, and plopping it perpendicularly to the real number line, right? And then you're going to get something called the complex plane. So let me write it down. This is the complex plane. So there's the x-axis, which is the real axis, and the y-axis, which is the imaginary axis. So let's look at point P, for example. Point P is 1 plus 2i. So you will associate this point P with 1 comma 2 in rectangular coordinates or in a complex plane, and this would be over here, point P. 2P, well, what you're going to take P and you're going to multiply it by 2, you're going to get 2 plus 4i, which will be associated with the point 2 comma 4, and this is the point comma here is 2P, right? 5P, we're going to, I mean, I hope you understand it. This is 10 plus 10i, which is 0.5 comma 10, right? And you're going to go 1, 2, 3, 4, 5 this way, right? And I don't know, I think it's something right here. Nope. All right, okay, so then if we want if you look carefully, right, you notice, right, that if you were to create a straight line, right, this straight line is going to pass through all these points. Okay, and the reason why is that when you have a complex number p, if you multiply it by a constant, all it does is scaling. So you're gonna just move it further away or closer to the origin. Okay. Furthermore, if I were to multiply p by, let's say, negative number, like let's say -3, right? This is not here in the list, but I'm just gonna write it down. So -3p is gonna be right here. So it's gonna be the exact same line, except going in the opposite direction. So if you want to go in the opposite direction from the origin, right, you're gonna multiply p by a negative number. So essentially, p multiplied. If you take this line is essentially k times p, right? It's a collection of all complex numbers, right, which are scalar multiples or like some number, some real number times p. This is the green line. The green line is like p times some number, like 3, 7, negative pi, whatever. So if you put all those numbers together, you're gonna get the green line. Okay. Now q. Let's practice again. Let's say 3q. So it's gonna be 3 minus 3i, right? And this over here would be q, right? Okay. And this is essentially plotting. Okay. Now let's plot 3q plus 5. Well, 3q plus 5p, right? So 3q is 3 minus 3i, 5p is 5 plus 10i, right? So if I were to uh, add them, right, I'm gonna get 5 plus 3 is 8. 10 minus 3 is 7, so it's gonna be 8 plus 7i. Let's see if I can count that. 1, 2, 3, 4, 5, 6, 7, 8. Right. 1, 2, 3, 4, 5, 6, 7. So it should be over here. So this should be 3q plus 5p. Okay. All right. Okay. Now let's look at this a little bit more critically. Okay. So what does it mean to add a complex number to another complex number? Okay. So let's look at this, for example, 3q. 3q is 3 minus negative minus 3i. So essentially, if I start at any point at the origin, q is go 3 to the right and go 3 down. Now, if instead of starting at the origin, I want to start at 5p, I would go 3 to the right and then 3 down. Well, look at that. You're going to end up exactly where you're supposed to, right? So if I were to represent Q by a vector like this, which represents moving 3 to the right and 3 down, I can take this vector, move it over here, which represents exactly the same complex number, adding 3 in real direction and -3 in the imaginary direction, right? Or, I mean, since addition is commutative, I could take Q and add 5. Wait, did I? 3Q, sorry. This is not Q, this is 3Q. I can add 5p and add that to 3q, and I will end up at the same place. Okay. Alrighty. So what about this? What about -3 minus 5p? So what is that? That is the opposite of 3q plus 5p. So it's -8 minus 7i, right? And essentially, this is a reflection of this complex number. Move things around a little bit so that we're not as cluttered. It's p over here. This is 2p, right? And this over here, this complex number, sometimes called the resultant, is 3q plus 5p. Notice that I can label the complex number. I can label this point, or I can also label the vector, and it is understood that they mean the same thing. Now, if I were to subtract or 3q plus 5p from 0, I will do the same thing as getting -3q minus 5p. Essentially, I'm going to get the reflection, right, which is -8. I count the squares quite slowly. I get here. So if I get the reflection, which is a nice color, we haven't used yet. Let's say light blue. So this over here is going to be -3q minus 5. So the reflection, or I'm just going to put the minus in front of the whole complex number. Okay? All right. Now, what is the conjugate of 3q plus 5p? So this essentially conjugate means you take the imaginary part and you switch its sign. So the conjugate would be 8 minus 7i. Let's see what it looks like graphically. So essentially 8, the real part stays the same, but the 7i, which was positive, now becomes negative, right? So the number is going to be the same location vertically, but sorry, horizontally, but vertically it's going to get reflected. So this is 3q plus 5p bar, the conjugate of it. So let's use some new color. I don't know, how's orange? Is orange any good? Yeah, orange is pretty good. All right, okay, so you see, these are all different operations and complex numbers, and this is what they look like graphically, okay, which I think is pretty cool. Okay. Now, next up is graphically and algebraically determine magnitude of P. Now, to remind you, what is the magnitude of P? This is the length of vector P, or distance of P, or from P to the origin. Now, this is also sometimes known as magnitude of P. Right? They all mean the same thing. Okay. If you remember, the definition was P, right? P was square root of a squared plus b squared. Well, let's make it z. So if z is complex number a plus bi, then its magnitude is given by that thing. Square root of real square part square of the real part plus the square of the imaginary part. Now, how does it work graphically? My diagram gets a little bit cluttered, so I'm not sure I want to do that. So I'm going to look at, let's say, 3q plus 5p. Let's look at this. This right triangle right here. If I want to figure out how far this point 3q plus 5p is from the origin, right, there's the real part and the imaginary part, and essentially this is the distance formula. So the length of the hypotenuse is going to be square root of a squared plus b squared by the Pythagorean theorem. Okay? So this is how you can see from from the diagram, from the complex plane. This is why it makes sense to define the magnitude this way. Okay? Because really in the complex plane, this is just the distance formula from the origin. So the complex number from the origin. Okay? And well, if we look at this, okay, so we want magnitude of P, right? So it's going to be a right triangle. So there's going to be, I'm just going to recopy it over here. So there's this P, right? This is P right here. This is length 1. This is length 2. So hypotenuse becomes square root of 5, right? So the magnitude of P is going to be square root of 5. If I look at the magnitude of 5P, I'm going to draw a triangle, right? And it looks exactly the same, right? Except it's scaled, right? So 5P, what is 5P? 5P is 5 horizontally, 10 vertically, right? So the hypotenuse is going to be 5 times of the magnitude of P. So magnitude of 5P is just going to be 5 times the magnitude of P, which is 5 to 5. Okay? And that's essentially it. And I mean, graphically, all of these values should be the same. Okay, so I'm skipping this one. Minus 3q minus 5p. I'm skipping it. It's like not that important, but these are important. Okay, so realize that 3q plus 5p is right here. If I take the opposite of it, this is the exact same vector reflected through the origin. If I take the conjugate, it's the exact same vector reflected through the positive x-axis, or x-axis in general. So even though these numbers, these complex numbers are all different, the distance from the origin is the same. So the magnitude of all these numbers should be the same. So let's see, what right triangle do we have here? 3q plus 5p is 8 plus 7. So this is the right triangle that we have here is going to be 8 horizontally, 7 vertically, right? So the hypotenuse is going to be square root of 8 squared plus 7 squared. 8 squared is 64. 7 squared is 49. If I add them, I'm going to get square root of 50 plus 60 is 110. So it's going to be 113. I think 113 might be prime, definitely square free. So I guess that's it. Unless I'm making a mistake, which I think I'm, but if I am, then who cares? All right, okay, so, but this means that all of these guys are also square root of 113. Okay? All right. Let me double check. 6 was 40, yeah. Okay. All right. Okay.